Can you see my screen now?
For the time being, we see you.
Went wrong. Let me try again.
It's coming. Now, yes, we can see it.
Yes.
Okay.
Yes, perfect. Thank you.
All right. So once again, thank you for the invitation and a nice introduction. So today's topic is continuous flow molecular sieving in organic solvents. Let me just change my pointer. Okay, I think that's better. Okay, so here is the outline of my presentation. First, I will give an overview about KAUST and the membrane center where I work. And I will briefly discuss the research interests of my group. And then I will talk about organic solvent nanofiltration and different processes, including organocatalysis coupled with separations using membranes in organic solvents, solvent recovery, catalyst recycling, reagent recycling. And if time permits, then I will also talk about the development of green and sustainable robust membranes. So let's see how far we can get today. Okay, so KAUST is based in Saudi Arabia. We are located on the Red Sea right here, not far from the city of Jeddah. So here you can see KAUST. This is a university town. So we live here, we work here, and we do everything basically within KAUST. Here you can see the community area. This is actually the Red Sea on the left, and here there is the desert. The campus is where we work. We have a town center, and this is the industrial area. We have a couple of companies on the university premises, such as Saudi Aramco and Dow Chemicals and SABIC, that we collaborate with. So the university in numbers, we have about 1,000 students, and we have a relatively good student to faculty ratio of 6 to 1. We are a postgraduate university, so we have mainly master students and PhD students, actually more PhD than master, as you can see here. And we try to take care of gender balance as well, so we are recruiting more and more female students and staff. And we have overall more than 100 different nations studying or working here at KAUST. Okay, so we have 3 different divisions, and I work in PSE, which is the Physical Science and Engineering division. And within that, we have 5 different research centers. And I belong to the Advanced Membranes and Porous Materials Center. So here you can see our building. This is building 4 on campus, and our center is located in this area mainly. This is another view of our campus and building 4 where we work. This is where I am at the moment. And here you can see some keywords about the research areas that my group focuses on. So obviously this is organic solvent nanofiltration that I mentioned before. And we develop different processes. We are interested in catalysis and catalytic membrane reactors, in molecularly imprinted materials, and the sustainability and green aspects of these. Okay, so in a nutshell, the group is focusing on sustainable separations through the combination of polymer chemistry, material science, and chemical engineering. So we follow a bottom-up approach that you can see here. So we develop new chemistry and apply this chemistry to develop new materials, mainly membranes and adsorbents, and then use these separation materials in innovative processes. And these processes are mainly performed in organic media. So this includes catalyst recovery, purification of drug molecules, pre-treatment of industrial waste, produced water treatment, and so on. Okay, so what is organic solvent nanofiltration? So organic solvent nanofiltration, or in a short form OSM, focuses on the separation of solutes in organic media by the means of pressure gradient through the membrane, and it can separate solutes that fall within the range of 100 to about 2000 gram per mole. And here you can see a typical cutoff curve for this type of membranes, where you have the rejection on the y-axis and the molecular weight or the pore radius on the x-axis. You can see that the small molecules, they have small rejection, so they penetrate through the membrane, and the large molecules, they cannot go through the membrane, so they have a high rejection. And the objective of recent years of membrane research was to obtain membranes that are more reproducible, they are tighter, so they have a sharper cutoff at low molecular weight, they are more stable in extreme environments such as elevated temperature or high or low pH, or organic solvents including polar aprotic solvents, which are particularly harmful for polymer-based membrane materials. So due to these recent developments over the last decade, now we have better, faster, and stronger membranes, and this allows us to develop new type of processes. So today I will talk about membrane development a little bit from a sustainability perspective, and I will also introduce you a couple of different processes where you can apply these new types of membranes. So the first research I'd like to talk about is organocatalytic membrane reactors. So the idea is to do reaction, catalysis in this case, and separation at the same time. So imagine that you have a membrane with a given pore size, so you can do size exclusion separation, and at the same time this membrane acts as a catalyst to perform a given reaction. So in this case, you can see that you have compound A, which is the substrate, you have compound B, which is your reagent, and when it passes through the membrane or reaches the surface of the membrane, then it catalyzes the reaction and the formation of C, which is your product. So the advantage of these type of systems is reduced carbon footprint, because you need less energy to perform the reaction and the separation as a single unit operation, rather than doing one after the other. Okay, so in this work, we utilized polybenzymidazole. You can see the structure here. Polybenzymidazole is an emerging polymer in organic solvent nanofiltration because it is insoluble in most of the solvents, therefore an ideal candidate for filtrations in organic solvents. So the first step was the preparation of the membrane itself that you can see here. So we did membrane casting, then phase inversion in water at 2 different temperatures. And then we obtained this solid film, a membrane comprising of polybenzymidazole. So the next step was the propyrylation of this membrane in the presence of sodium hydroxide, which yielded this modified PBI, which is ready for click reaction. So in the presence of copper iodide and an organic base, we can click any azide onto this propyryl group. And in this case, we took this cinchona alkaloid and modified it so it contains an azide group here. Okay, and this azide group can react with your propyryl group, resulting in this triazole-linked organocatalytic membrane. So we did basically covalent anchoring of the catalyst, the organocatalyst, onto the membrane surface. So why is that important? In previous studies, the catalyst, whether it was an organocatalyst or a metal-based, a noble metal-based catalyst, they were always dispersed into the dope solution and then cast, which means that it can leach out during the application, and eventually the catalytic performance deteriorates, and the leaching catalyst can also contaminate the final product. So we deduce that by the covalent anchoring of the catalyst onto the membrane, we're not going to have any leaching of the catalyst, so we can perform all of these catalytic reactions at a constant TON or TOF turnover number and turnover frequency without the deterioration of the catalyst and the contamination of the product. Okay, so due to the lack of time, I'm not going to go through all of these slides in details. Basically, what we did next is we focused on the characterization of the membrane in terms of chemistry and morphology. So you can see here that the membrane that we obtained is an integrally skinned asymmetric membrane. And the catalyst is basically incorporated into the membrane throughout the surface and the cross section. Okay, because it was anchored basically everywhere that is propagated, so throughout the membrane. And we looked at different techniques to actually prove this. If you're interested in the details of this work, then I recommend our publication. Here you can see the details. Okay, so now let's focus on the actual performance of these membranes. So the catalyst is well suited for Michael addition and Osm-Michael addition reactions, and this is what we focused on. You can see here the model reactions and the substrate scope. We changed the R and X and Y groups, so we tried a wide variety of compounds successfully. And here I need to note that the catalyst that we used, that you can see here, is an asymmetric catalyst, which means that we are going to have, luckily, a product that is enantiomerically enriched. Okay, so this is an asymmetric catalysis that we did. And therefore, we are interested in two different parameters when optimizing the catalytic membrane reactor: the yield of the product and also the enantiomeric excess of the product. Okay, so how much more R enantiomer you get over the S enantiomer. And here you can see the summary of these two parameters as a function of the actual reactor. So we have reactor A, B, and C, and 1, 2, 3, these represent the different reaction entries that you see here on the left. So these are the different model reactions, and A, B, C are the different reactors. So here you can see the reactor summary. So first, we were interested in using the original organocatalyst without any modification as a homogeneous catalyst dissolved in a solvent, and then we performed the reaction. So that's our benchmark, basically. That's A. Then we have the membrane catalyst in a stirred tank. So in that case, we prepared our catalyst anchored membrane, but instead of applying it under pressure and doing any filtration through the membrane, we took this catalytic membrane, placed it into a stirred tank, and then basically used it as a solid supported catalyst. Okay, so now from moving from A to B, we move from homogeneous catalysis to heterogeneous catalysis. And ultimately, we tested our membrane in a catalytic membrane reactor, where you place the catalytic membrane inside a nanofiltration rig, you apply pressure, and then basically you're going to end up with a permeate stream, and you're going to end up with a retentate stream that you recirculate. Okay, so that's the catalytic membrane reactor, and this was our ultimate goal, to apply the membrane in such configuration. So now we can compare the result of these three membrane reactors by looking at the yield and the EE value, the enantiomeric excess. So what are the conclusions? Instead of going through all of these reactions one by one, what we can say is that the yield is overall between 69 to 94%, which is relatively good. And the EE value is 90 to 99%, again, quite high. You can see that in some cases, or actually in all of the cases, when you move from the homogeneous catalysis, which is the blue bar, to the heterogeneous catalysis, then you have a drop in the yield. Okay, so these are different bars. So always going from blue to red, you have a drop in yield, which makes sense because you're moving from homogeneous to heterogeneous catalysis. But when you move on to the last reactor, where you apply the membrane under pressure and you have permeate and retentate flow, then the yield goes up. Okay, so this means that we can circumvent the problem of moving from homogeneous to heterogeneous catalysis by using proper membrane reactor, where we have a flow not only tangential to the membrane, but also through the membrane by applying pressure. And if you look at the enantiomeric excess, basically what we were assuming, our hypothesis, was that the EE value not going to be affected because the active site of the catalysis is intact. So when we designed this catalyst to be anchored onto the membrane, we added an azide group, but that is far from the catalytically active site of the catalyst. And therefore, it should not interfere with the catalysis. Okay, this was our hypothesis. And based on the actual data, if you look at the EE values, then they are more or less the same. They're all between 90 and 100%. So we can safely say that we did not basically damage the catalytic activity of our catalyst, and it is still suitable for asymmetric catalysis. And of course, if you look at the different reaction entries, then you have different enantiomeric excess, and then 7 and 8, basically these two reactions gave the highest enantiomeric excess. Whereas when you look at 1 and 2, with these particular reactions, the enantiomeric excess somewhat got lowered because of the presence of the this tetrazole group after the click reaction very close or relatively close to the active site of the catalyst. Okay, so then we were interested in actually understanding the fundamentals at a molecular level. What is happening with the polymer chain? What is happening with the catalyst? How do they interact, the polymer and the catalyst and the catalytically active site? And how is that affecting the actual substrate and reagent interaction? So we had a collaboration with Furukawa Electric, with Tibor Holzel, and this is mainly his work. He's the one focusing on DFT simulations. And basically what we concluded is that the presence of the polymer chain is not significantly affecting the configuration of the catalyst. But we also observed that in some cases that you saw in the previous slide, where we had a relatively high, or still very high enantiomeric excess, in those cases, the catalyst actually, the modified catalyst, allowed the reagent and the substrate to get closer in a more favorable angle during the reaction. And this is why we assume that we still have a very high enantiomeric excess in those type of reactions. So basically here, the DFT modeling and the actual catalytic performance obtained in the lab, they come hand in hand, and they are in good agreement with each other. Okay, so then we were looking at the process design, and we wanted to optimize this membrane catalytic reactor. So we turned to a design of experiments. Instead of doing a trial and error, we used the central composite phase model with 30 runs, and the objective was to minimize the reaction time, minimize the pressure that we need, and the recirculation. Okay, so the recirculation is basically the flow rate of the recirculation pump in the system. So if you look at the catalyst or membrane catalyst here, then you have a tangential flow, that is the recirculation, and you have a perpendicular flow, which is basically the permeate, that's the flow that goes through the membrane. And if we can minimize the pressure and minimize the recirculation, then we can save energy and ultimately have a lower carbon footprint for this process. And the criteria was to maintain the conversion higher than 99%. So here you can see the conversion. That's actually the contour plot. And we have on this axis the recirculation in liter per hours. We have the pressure on the x-axis, which basically translates to the obtained flux, because we kept the membrane area constant in this system. And we also changed the reaction time, 6 hours, 12 hours, and 24 hours. And at the end of this optimization, with the design of experiments model, we concluded that the sweet spot is actually this one here, which gives us 30 bar and recirculation of about 90 liter per hours. And this is the corresponding flux. And here we managed to minimize the parameters that we wanted to minimize and still keep the conversion quasi 100%. Okay, so here you can see the actual catalytic membrane reactor that we have in the lab. So we actually have two of these membrane reactors. One is coupled with an inline FTIR, and the other one is coupled with an inline NMR. So with process analytical technology, we can actually continuously follow the reactions that we perform in these reactors. And I wanted to show you a close-up. So here you can see membrane cells. This is where you have your catalyst or your separation membrane. Here are the permeate flow rates. And this is the recirculation loop with the recirculation pump head that is sticking out from the bench. So this was the recirculation flow rate that we were optimizing. And we have a high pressure pump somewhere below the bench that you cannot see from here, but this is the feed that is coming up somewhere behind the valve. So that is the system. And here we have a continuous reactor, either a packed bed reactor that we can place inside here, this housing, or a coiled reactor that can be connected to the membrane separation unit. And we will see examples of the combination of this reactor with the separation unit in the upcoming slides. Okay, so then we looked at the separation performance of this membrane. So first we characterized in terms present the different compounds that we have in a crude mixture, and we want to separate. So we have two different membranes that we prepared, A and B, at different temperatures, and they have a slightly different rejection profile, which means that they are better suited for the separation of different compounds. And of course, the larger the gap in the rejection, the easier and more sustainable the separation will be. So we needed a reagent excess for all of these reactions. We are using 2 molar equivalents of the reagent, which means that eventually, if we have 100% conversion, which we almost have 100%, then we're going to end up with 1 equivalent remaining reagent, which is contaminating the product, so it needs to be removed. And therefore, we need the purification step. And here you can see the actual process scheme for this catalytic membrane reactor. So in these vessels, third vessel, you have your substrate and your reagent. You perform the reaction by using this pump and pressurized system. The retentate is being recirculated back, that you can see here on the top. And we have the permeate going through the membrane, which is also recirculated back. Okay, and this is the catalysis stage. And once you completed the catalysis, then you end up with the crude product. Okay, so at the beginning in this unit, you have reagent and substrate. It is converted into a crude product, and then we have to do the product purification. So eventually we're going to end up with a pure product in this line. So to go from crude product to pure product, we have to purge out this extra 1 equivalent of reagent. So to purge it out, we use diafiltration, and 10 diavolumes was needed to achieve a high purity product. And the permeate stream was diverted to another membrane unit. Okay, so you could just discard that permeate, having your reagent, but what if we want to recover that and reuse it? So from a sustainability perspective, it's important to recover your unused excess reagent. So in the second unit in this membrane cascade, we had a tighter membrane. This is membrane 8 here. And this allowed us to recover the substrate and to recycle the solvent back to the original system. Okay, and by doing so, we can reduce the solvent consumption, and we can also reuse the substrate if we wanted to. So here you can see the concentration profile during this operation. This part is the catalysis, okay, at the beginning, where you have this valve open to the left. Okay, so this is when you recirculate the permeate. And then after the completion of the catalytic stage, then you swap this valve to the right, and then you start the separation. So then the permeate is diverted into the second stage of your membrane cascade. And we were monitoring all the compounds in the system, including reagents, substrate, product, and we monitored where they go, where they end up, and we closed the mass balance basically. Okay, I'm not going to go into more details about this, otherwise it would take too much time. Okay, but just to conclude here, we compared the sustainability of this reactor with 3 different case studies. So case 1 is when you don't apply the solvent recovery stage. Okay, so that's basically only the top part of this scheme. Forget about the second one, the permeate goes to waste. Case number 2 is when you apply solvent recovery, so you do have a second stage, and you reuse the substrate that you're recovering from the second stage. And in some cases, when the substrate is not pure enough, then, and you want to meet pharmaceutical quality, then you cannot recover, and you can recover, but you cannot reuse the substrate because it's not pure enough. So in that case, you have to discard it, and this is case number 3. So what you can see here is the waste generation and also the equivalent CO2. So this is basically the carbon footprint per kilogram of product in both cases. So you can see that the bottom line of these 2 comparative tables is that the solvent consumption is the main issue with all of these membrane separations and purifications. So therefore, it's extremely important to recover your solvent. And what you can see here is that the E factor significantly went down from 141 to not 0.000405. And this is when we are reusing the substrate. So if you're not reusing the substrate because we have some purity concerns, then we end up with a higher waste generation, but this is still significantly lower than without the membrane operation. Okay, so it's up to you if you want to reuse the substrate or not. Just by recovering the solvent, you can significantly reduce the waste generation. And a similar trend is observed for the carbon footprint that you can see here. Okay, so in this example, this is another example of a membrane reactor, but the example that I have shown you so far focused on having a membrane with a catalyst incorporated into it. Okay, and there we had to do the catalysis first, and then we had to stop the reaction and carry on with the purification. Okay, so that goes in stages, alternating stages. In this particular case, you have a reactor on its own that you can see here. That's a flow reactor, a packed bed reactor. And that is coupled to a nanofiltration unit that you can use for solvent and reagent recycling. Okay, and this system is truly continuous. You can continuously feed in your substrate and reagent and obtain your crude product, purify it, and take away your purified and concentrated product while you're recovering your solvent and the excess reagent. Okay, and in this case, the catalyst is not on the membrane, but it is in the packed bed here. Okay, so you can see the effect of the in situ solvent and reagent recovery, so this unit here, on the E factor and the carbon footprint. So you can see that you can achieve a 91% reduction in the E factor if you're applying solvent recovery, and a more modest reduction in the overall carbon footprint, okay, which is 19% in this particular case. Okay, so again, we have demonstrated that with a different catalytic process and a different process configuration, you can reduce the E factor, basically the waste generation of your process, as well as the carbon footprint. So the main difference between the E factor and the carbon footprint is that the E factor is taking into account the waste generated, while the carbon footprint is taking into account the waste and also the energy that is needed for the process. Okay, so you can see that this is the E factor and what was taken into account. And you see the carbon footprint, which is larger because it also incorporates the different energy usage for the pumps and the thermostat for the reaction. And here's another example where we used a plug flow reactor. Okay, so this is a coil tube plug flow reactor. And the previous two examples were heterogeneous catalysis. Okay, so we took a membrane material and we grafted an organocatalyst onto it. So you have a membrane and that is the catalyst. So that's heterogeneous catalysis. In the second case, we had a packed bed reactor with a solid catalyst in it. So again, that's a heterogeneous catalysis. But we can also do continuous flow membrane reactor separator hybrid process by the combination of a plug flow reactor and a nanofiltration unit. So in this case, we have a coil tube reactor, which is about 10 meters long. And within that, you have a continuous flow of your catalyst through the system, which is being recirculated, okay? And it does not go through the membrane, so you need a large catalyst, which is still solution processable. And in the permeate, you can collect your product. Okay, so to enable this process to happen and fully recover the catalyst and keep it in solution, you need to have an anchor for your catalyst. Okay, and in the literature, you can find many different types of catalyst anchors, mainly polymers, onto which you can attach your catalyst. So in this particular case, again, we wanted to consider sustainability not only at the process scale by recovering the solvent and by purifying the product, but also by a means of catalyst design. So in this case, we turn to cyclodextrins that you can see here. It's a naturally occurring sugar-based molecule, therefore sustainable. And we modify this cyclodextrin by adding the catalyst onto it. Okay, so now what we have done is we significantly increase the molecular weight of the catalyst, and therefore it is not going through the membrane, and you can easily recover it in such continuous systems. Okay, so here you have your substrates, or substrate reagent 4 and 5. Here you can see the structure, and 7 is forming as the product that you can see here at the end of this process. Okay, and the first step is going through the reactor, and once the reaction is complete, then the retentate is in situ recycled back. Okay, so the catalyst and the solvent is going to be recycled back. The issue that we initially obtained is that the reaction is running at about 20 degrees Celsius. And at that temperature and at high concentration that we were working at, the product crystallizes out from the system and blocking your plug flow reactor and blocking your membrane surface. So the solution to that was to increase the temperature locally in the membrane separation unit up to 50 degrees Celsius, and that allowed us to keep the product in solution and avoid any precipitation and clogging of the membrane and the reactor itself. So this is the final process that we obtained here. Okay, and in numbers, we achieved virtually 100% catalyst recovery, high enantiomeric excess again, high product purity, and we have performed this continuous operation over 18 days and obtained stable performance. So again, if you're interested in the details of this work, then I recommend our publication on this research. And this is the last membrane reactor, or actually this is a membrane extractor, but also in continuous flow with a similar concept that I just introduced to you. So here we were focusing on the extraction of pharmaceutically relevant compounds from agricultural waste. In this particular case, we were working with a company in Turkey who's producing olive oil from olives. And during the olive harvest, the tree is beaten and all of the leaves are falling on the ground, and those are collected and are considered as agricultural waste, and they are utilized as animal feedstock. Okay, but we know that not only the olive oil and the olive itself, but also the leaves are full with valuable compounds, antioxidants, and so on that could be utilized. So we developed some adsorbents that were used to selectively isolate oleuropein, which is an antioxidant, from this waste material. And without going into the details on the adsorption and the adsorbent material, let's just focus on the membrane part. So the crude product is actually going onto these adsorption columns continuously, alternating between high and low temperature, so basically between adsorption and desorption. And when you do adsorption, then basically your product getting adsorbed onto the column, which means that the waste is going through the column. So then this waste is going into a nanofiltration unit where we concentrate it, and eventually we end up with a concentrated waste in this vessel. And at the same time, when the waste gets concentrated, then we obtain a relatively pure solvent that can be recycled. So that you can see here in the permeate that the solvent is being recycled. Parallel to this, on the desorption column, we are washing this column with the pure ethyl acetate in this case, and that at high temperature, which means that your product, your valuable product, is being desorbed from the column and flows into another nanofiltration unit where you concentrate this product and at the same time recover the solvent. Okay, so we end up with a concentrated product here that we cool down and it crystallizes out and we obtain oleuropein. Okay, so this is another type of example that shows how nanofiltration and organic solvent nanofiltration in particular can be used to recover solvents in a continuous way and therefore reduce the effector and carbon footprint of your process. So again, we looked at the effector and the carbon footprint, and we obtained a significant reduction in the effector, and again, a somewhat lower, actually half reduction in the carbon footprint. So here, if you look at the carbon footprint, it includes the energy consumption, and you can see the red, blue, and green parts of the bar are quite high, and these belong to the thermostat. Okay, so the thermostat itself is consuming quite a lot of energy. Here we need 10 degrees Celsius, here we need to maintain 25 and 43. Okay, but don't forget that once you scale this up, then in an industrial case, you always have heat that you can actually recycle, and therefore you're going to have a much lower energy consumption in a real case. Okay, so now it's 3:47. How much time have I got? Should we stop here with these processes, or shall I move on? Because the next topic is a little bit longer. Ludo, what is your suggestion? You said I have about 35 minutes.
Yeah, I think if you want to go forward next, 5 5 to 6 minutes. That's okay. We still have time for questions after. It's really up to you, Georgie, if you want to stop there or if you want to go through part of your other works there. We still have time for questions afterwards, I think, if you want to keep going for a bit.
Okay, so then I would suggest to stop here because this presentation so far was focusing mainly on processes and a little bit of membranes. And then basically the next project that I wanted to talk about is more about membrane fabrication and how to obtain green membranes and so on. But maybe that can be another presentation in the future because otherwise it would
we can invite you another day for sure.
Sounds good.
Very interesting.
Thank you very much, Georgie, for a very nice talk.
Only polymers were used that are really insoluble in organic solvents. So of course, most of the polymers, they are soluble in polyaprotic solvents. So you can use those solvents to prepare the membrane itself. And then you can use it in many other type of solvents, such as esters, alcohols, ketones, and so on. But you cannot use them in polyaprotic solvents. Yep. So the next step was to come up with ways of stabilizing them, such as cross-linking. So if you cross-link your polymer chains, then you're going to end up with a cross-linked polymer network, which is insoluble in everything, and therefore you can use it in more or harsher environments. And nowadays, in the last decade or so, there are different approaches besides cross-linking. So I would say that the other 30 years focus mainly on cross-linking, and nowadays there are different innovative solutions related to polymer chemistry and surface modification of membranes. So one of them is the use of interpenetrating polymer networks that can give you a membrane which is solvent stable. Another way of doing it is not necessarily you need to cross-link the membrane with a bifunctional coupler, but you can actually use acids and monofunctional doping basically of your polymer that results in polymers that, let's say, are slightly soluble in water, but they are not going to be soluble in organic solvents. And that's a very relatively simple way of stabilizing your membrane in organic solvents. Another way, which is really a hot topic nowadays, is carbonized membranes. So there are not many membranes reported on the use of carbonized membranes in liquid separations. They are mainly used in gas separation, but that's another area that could provide some solution to the problems of stability of membranes. Regarding aging, it is indeed an issue. And the problem is that there are not many reports on the long-term stability or aging of organic solvent nanofiltration membrane. So if you look at the literature, then most of the studies are, I would say 90% of the studies report membrane performance over a couple of hours or maybe a day. And already when you're looking at 1 week or 2 weeks of continuous operation, then you have maybe, 1 to 5% of the papers. And then if you look at a month or more than 1 month, then I can count it on my one hand, how many papers are reporting really long-term stability or performance of membranes. And therefore, it's very difficult actually to do research in that area because we don't even know what are the issues and which type of polymers and membranes have what kind of issues in different solvents. So that's a whole new area that should be explored. And your last question was about the industrial application of OSM. Basically, there is not much direct information on that. If you look at the patent applications, then you can kind of guess which industrial sectors are using these membranes. And there is an increasing number of patents coming from industrial, basically companies, which is promising. And the applications include solvent recovery that I know of, include solvent recovery and catalyst recovery. So these are the main applications nowadays, but also biofuels. The application of OSN in biofuel purification and separation is also emerging. And there are some interests from petrochemical industries for the pre-treatment of diluents and other type of streams that they have on large scale.
That's great. Thank you so much for this answer. We have two more questions here. So one, which is on the main chat, which I think can really read if you want, Georgie from Diagonal Seni. So I just read it aloud for everyone, but quite a bit of your previous work was on pharmaceutical industry. Would you say that OSN is promising for genotoxic molecule removal or API isolation in industry? Are there any particular cases you could think to be useful to look at or look into?
Okay, so my brief answer, if you're interested in this area, please get in touch with me, because actually that was a topic that I really focused on for more than 3 years. I worked in the pharmaceutical industry, and my focus was the removal of genotoxic impurities from drug formulations. And OSN is really well suited for these kind of purifications, because genotoxic impurities are usually quite small and the APIs are large. So it makes sense to apply size exclusion membranes in organic solvents to do these purifications. And we filed a patent on this specifically, the use of OSN for API degenotoxification. And I know that Hovion is using it at the moment.
There was a question sent to me, so which I think Lourdes put that down as well. So very interesting topic and nice talk. Thank you. How do you see CO2 reduction, so CO2 conversion potentially in this type of membranes, such as converting CO2 into chemicals selectively by these catalytic separation processes?
Again, that's a very interesting area, and I was also thinking about actually going into this area, although we haven't done any work on it. But I see also a huge potential, because again, when you do CO2 conversion, then the molecular weight difference between your product, your reagent substrate, is going to be different, and then therefore you can use OSN to purify your product and so on. So I think it's an interesting area.
I agree. There's a few papers that came out actually recently. Quite a number have looked at amine-based solvents used for CO2 capture, but recently looking at the conversion or degradation by products from carbamide formations. I think it's definitely a nice topic. Another question from Arjun. I am comparatively new to this area, but how could we calculate the CO2 produced for a process? I think it does refer to one of your slides, maybe, where you were looking at the footprints, I guess, of a process. So could you please comment on that?
Yes. So basically, for the processes, you need to take into account the that you're generating. Okay, so we have different type of waste. So in processes that I showed today, you need to take into account the membrane material. That's going to be a waste at the end of your process, right? Because that's a consumable. So you have the membrane material, you have the solvent, you have any leftover reagent, byproducts, side products. Those are all waste that you need to take into account. Mainly the solvent will determine your waste actually. And then you have to take into account the energy consumption. And for that, you need to know what is the energy consumption of the pump. You actually have two pumps, the high pressure pump, you have the gear pump for the recirculation. If you need to use any thermostat, then the energy requirement of the thermostat. And then basically there are different ways to convert both the energy consumption and the waste generation into equivalent CO2. It's called the equivalent CO2. And for that, you have different platforms. So this is something standard that you do. There is CCOG, for instance, if you're interested in that was developed at the University of Manchester. There's a sustainability group by Adisa Azapajik, and she's focusing on life cycle assessment. And basically, if you use CCOG, you can put in a given solvent, the amount of the solvent, and it will calculate the equivalent CO2. And of course, if you're using a halogenated solvent, then that's going to have a different factor and a different carbon footprint compared to, let's say, using something that is from a bioethanol, that is from a renewable source and not halogenated and so on. Okay, so there is quite a lot of information or science behind it. It's not that easy, but also not very complicated. So first you need to understand your own system and what you have, and then you need to start converting it into equivalent CO2 and then sum it up.
Thank you. I think it fits well with We have a question we have had from, again, Yanya Seni, who is asking about the life cycle analysis, which you showed partly in your talk today. And if you are considering also, here have a membrane manufacturing process, I guess, here in that life cycle analysis, or in the waste being generated, and potentially going beyond the question, and probably there is not enough data, but if you also consider the end of life of the materials, depending on how quickly they could age, and again, if that's something you have looked yourself in terms of LCA so far.
Yes. So basically, when we run these calculations, then of course we have to assume what is the lifetime of your catalyst, what is the lifetime of your support, what is the lifetime of the membrane, and again you have to turn to the literature and try to find some information on how long these membranes can be used for. And this is very debatable and very difficult to judge. So this actually gives you quite a lot of or quite a large error in your calculation. So let's say in organic solvent nanofiltration, if you're using your membrane in a very harsh solvent or a very mild solvent, then of course the lifetime of your membrane can be totally different, spanning from 1 year to up to a couple of years. Okay, and that will change, of course, the base generation and then the carbon footprint. However, the membrane itself is so small, and when you burn it, you incinerate it, then this generated CO2 is so small compared to the solvent that it becomes negligible. Even the error that you have, if you assume 1 year of operation or 5 years of operation, is not going to make a huge difference. Okay, because always the solvent that you need when you do purification of your product and diafiltration, then you just need to keep pumping fresh solvent into the system to achieve high purity.
Yeah, that makes complete sense. Thank you so much. I don't see any other questions coming from the audience. We had quite a few, which is great. So I think we might just draw a close for today's Reach seminar series. I would like to thank once again Georgie